Today we're going to be talking about baseball and baseball extensions of the baseball idea and the use of network flow. And the basic result on baseball and network flow we talked about previously. So today I'm going to be talking about a more advanced issue involving the baseball question and the end of season kinds of questions. So the first thing is, let me just remind you what the basic setup is. And I'm going to do this in a way that generalizes from baseball to all different kinds of games. So in a game, you have a payoff or set of payoff, I'll call them pairs. This is just going to be a game between two teams. These payoff pairs indicate what are the possible outcomes in terms of scores, in terms of in terms of what the teams accumulate. So in baseball, you either get one win or 0 wins out of each game. So each game gives, if you want to think of it as, gives 1 point to one team and 0 to the other team based on who won that game. And then over the entire season, whoever has the most points, which is equivalent to whoever has the most wins, that's the league leader or the season winner. But in a single game, each team, one team gets 1 and one team gets 0. And so this is the payoff pair for baseball. Now, not all types of games have that kind of payoff pair. So, for example, I think 2-0-1-1, this is the typical setup for what? For hockey. Okay? So in hockey, games end either in a win for one team, in which case the winning team gets 2 points and the losing team gets 0, or they end up in a tie and each team gets 1 point. Okay, so this is the payoff pairs that are possible in hockey. And then in European soccer, I guess it's, well, according to my notes, I don't really know if this is true, but in it's 3-0-1-1, and this is what happens in European, I'll call it football. Okay, if one team wins, they get 3 points, and the other team gets 0, and if they tie, they get 1 each. Okay, so here are 3 different payoff pairs that are possible for 3 different kinds of games, and there's unlimited numbers of payoff pairs I bet you could find. Well, I shouldn't say unlimited, but many, many different payoff pairs that you can find if you look at different kinds of games. And I'm happy to hear about some others that people might know about. Okay. All right, and so the issue is that the season is close to an end, and where you are close to the end of the season, most of the games have already been played, and therefore teams have a certain number of points they've accumulated, and yet there are some games left to play. And the question that comes about is, which teams have already been eliminated? Which teams have no hope of either winning the championship, the title, winning the most number of points at the end of the season, or at least tying for the most number of points? And so elimination means no hope of getting the most number of points or tying, even tying for the most number of points. Okay? And what we talked about last time through the use of network flow, recall, using network flow, we can identify the eliminated teams in baseball. So that means in the scoring scheme where there's a payoff vector or payoff pair of 1, 0. Okay? So there's a polynomial time algorithm, an efficient algorithm that identifies all of the eliminated teams under the baseball scheme. And it used network flow. Now what I'm going to do today is focus on two kinds of generalizations of this, or two extensions of this result. One is going to be a general proof, a theorem that refers not just to the 1, 0 payoff pair, but to many payoff pairs, including all the ones that we see here, and I'll explain in a minute what the set of payoff pairs are that are included. And it'll be a general result for that. And then we'll come back to baseball, and we'll look at a more precise question where we're not just interested in whether the team can win or tie for the most number of points, but we're interested in whether it can be the undisputed winner. That is, can it win with more games? Can it have more games, strictly more points than any other team? So we want to take this question but eliminate the possibility of tying. And it turns out that's a much more difficult question. So this is the classical question that was examined for 30 or 40 years even. And what I'll tell you about where we eliminate the possibility of tying is a much more recent result. Okay, let me also remind you that when we solved this through network flow, we were solving for each team independently. We were going to look at a particular team and ask whether that team was eliminated or not. And so we had to do a separate network flow for each team. But now we want to prove a theorem that is a little bit surprising, which says, in fact, you can get the answer for all the teams simultaneously. You don't have to focus on each team individually. But you'll see exactly what that means in a minute. Okay, so let me put up some notation, some definitions. Wi, actually this wants to be a little w, sort of a script wi, is the number of points that team I already has. So remember, we're close to the end of the season, and Team I has played various games, and out of the games, it's accumulated a certain number of points. In the case of baseball, the number of points is exactly equal to the number of games that have been won. But in the general setting, where you can get different numbers of points for winning or for tying, this is the number of points that Team I has already accumulated. And then GI is equal to the maximum number of additional points Team I could get in the remaining games. So we're just saying, well, if the best thing possible happens to Team I in all the remaining games, how many points would Team I get? And that's GI. And so therefore, we're going to define capital WI is equal to little wi plus GI. That's simply the most points that Team I could end up with, is the maximum number of points Team I can end the season with. Okay. And then, so with this notation, we're going to prove the following theorem first. Theorem there is a number W star such that Team I is eliminated if and only if Wi is strictly less than W star. So this is actually a theorem that was first proven in the context of baseball only, I think around 2004, by a student at that time at Cornell named Kevin Wayne. And it was very surprising because up until that time, when people thought about this baseball elimination business, they focused on each team separately. Each team separately, you would ask whether that team was eliminated, and you could solve that problem by network flow. And then when you asked about a different team, you solved that by a different network flow, and so on. But it turns out that all of those questions can be addressed together through this theorem. The questions of elimination for all of the teams are tied together. They're not separate and independent, because this number W star, that is independent of any particular team you're talking about. There's just one universal number that's based on the whole set of teams, W star, and it has the property that any team I, so this W star is not dependent on I, but now when we look at any team I, that's eliminated if and only if this number Wi is less than W star. So if we can compute W star, then we just look at each team, and Wi is obviously trivially computed. Wi is just little Wi plus GI, so that's a trivial computation. If that Wi is less than W star, then Team I is definitely eliminated, has no hope of either being the undisputed winner or tying for being the winner, of having the maximum number of points. On the other hand, if Wi is greater than or equal to W star, then in fact, Team I can be, under some scenario, some win-loss scenario of the future games for all the teams, or some outcome, some scenario with the payoff pairs for all the future games, then I can, in fact, either be the undisputed winner with the most number of points, or at least tie for the most number of points. That is if Wi is greater than or equal to W star. So everybody clear on what this is claiming and why this was a surprising result compared to what people knew previously, where it looked like the question of elimination had to be answered for each I separately. Okay, so now I want to prove this. And we're going to prove this, okay, so this is certainly true for baseball. And I want to actually generalize this theorem to a large set of types of games with different payoff pairs. And so I need to define a set of payoff pairs that we're going to look at, and then I'm going to modify this theorem. But this theorem is certainly true for baseball, hockey, European football. It's true for all the particular types of games we've looked at so far. So let me just do this definition, and then I'm going to modify the theorem so we can prove it abstractly in general without any particular type of game in mind. Okay, so definition, a set of payoff pairs is called monotonic if it is possible to move an outcome to one which is always possible to move an outcome or change an outcome to one which increases the points of one team without increasing the points for the other team. For the other team. Okay, so let's look at the various scenarios that we have, the various types of payoff that we have so far. So baseball, that only had one possible payoff pair. One team gets 1 and one team gets 0. So this trivially satisfied, monotonicity is trivially satisfied here because there's only one payoff. But let's look at another one. We have 2-0, 1-1. Okay, so this was from hockey, right? And what this is saying is that actually, it's always possible to move an outcome to one which increases the points without increasing the points for the other. I should have said unless you're already in the outcome where you've maximized the number of points possible. Okay, so if you're not already getting the maximum number of points possible, then you can move to an outcome where you do. So in this case, let's say the outcome was 1-1. Okay, each team gets 1 point. Then if we move to this outcome, one team is increasing, it's getting 2, and the other team is not increasing, it's moving to 0. It's in fact decreasing, so it's not increasing. Okay, so when one goes up, the other one either stays the same or goes down. And the same thing is, let's say, in 3-0, 1-1. If we move from here to here, then one team is improving, okay, and but the other team is actually going down. Okay, so whenever one goes up, the other one either stays the same or goes down. Now, most games, most types of sports that you can think of, will have that property. I don't know of any sport that doesn't have that that property, that when one gets more, the other one gets less or stays the same. I could imagine, however, let's say we had one where you had a 5-5 and, I don't know, a 3-0. Okay? So when you're here, one team's getting 3 and one team's getting 0, and then in order for one team to get 5, the other team also has to get 5. You could have games like that, I suppose, where if it was just such a wonderful game, if both teams were so spectacular, the judges just said, well, you were both so wonderful, we're going to give you both 5. Okay, it's possible. But if you're talking about points given for the outcome of the game, then that doesn't happen. Not points scored in the game. If you're talking about points scored in the game, then it's a different story. But at any rate, these are the outcomes that we know of for baseball, hockey, football, and I don't know what other sports we could look around. At any rate, if the payoff pairs are monotonic, then they have this property. Okay, so this theorem is going to be restricted to in sports where the payoff pairs are monotonic. Then there's this number W star, which is independent of team I, such that team I is eliminated if and only if Wi is less than W star. Okay? So we'll see in the proof of this that we need the monotonicity property at one point. And without the monotonicity property, we don't, it won't go through. Okay, so now we can prove this. Okay, so first of all, let me also say a scenario for the remaining games is what payoff pairs result from all those particular games. Who wins, who loses, what payoff pair gets generated from those particular games. Okay, so proof. Let S be a scenario for the remaining games. The games that are not yet played. And WS be the maximum number of points any team gets under scenario S. So we have some games left to play, and one team gets 3 points, the other team gets 0 in one of those games, and then another game, one team, they both get 1, and then another game, etc. And that's what scenario S is, and when you look at the total number of points that the teams get, WS is the maximum number of points any team gets when we're using scenario S. That WS is the sum of the points that the team has already gotten before we look at the scenario plus what they get under the scenario. Okay? So this is the outcome, the best outcome that happens to any of the teams when we finish the season with scenario S. Okay? And then let W star, no, WS star, no. W star be the minimum WS over all scenarios. So overall, the games that are left to play, there are lots of different scenarios that could happen. Who wins, who loses, which particular payoff happens in each game. And in each one of them, in each scenario S, there's some best thing that happens to some team, for some team, that's WS. And therefore, if you take all of those numbers, all those WS numbers, there's some minimum over all of those. And that's what we're looking at. We want W star to be the minimum WS that happens over all those scenarios. And we let S star be the scenario that scenario where WS star is equal to W star. So this is the scenario where the best outcome for any of the teams is W star. Okay? But again, S star, W star is the minimum WS over all the scenarios. Okay, so we have this little bit of convoluted definition, but if you think about it, you'll be fine. All right, so we have that. And I want to prove that this W star that I've just defined here has the property that's claimed in the theorem. Okay, so it's claimed in the theorem that there's a number W star, and here's what it is, such that any team I is eliminated if and only if Wi is strictly less than W star. Now, in this proof, it doesn't give you any hint as to how you would find W star. Okay, because this is the definition of W star is looking over all possible scenarios, and that's not very efficient. It's certainly finite, it's constructive, but it's not very efficient, and so this doesn't suggest whether finding W star is an easy process or not. We just want to prove that there is such a threshold W star. Okay, so to prove the theorem, let me erase part of the board. Let me go over here. Okay, so continuing the proof, if Wi, which after all was equal to little wi plus gi, if that's strictly less than W star, then there is no scenario where team I has the most points or even ties for the most points. Well, this is just really the definition of things. Wi was the best, the most points that team I could ever possibly get. This is what they already got, and this is if they do the very best in all the remaining games. That's what they get. W star, what's W star defined as? It's defined as the minimum over WS, where S is a scenario. It's the minimum over all possible values WS over all scenarios. WS is the amount, it's the number of points, the highest number of points that a team wins when we have scenario S. So in every possible scenario S, somebody is getting W star or more points. Okay, just by definitions, the definitions of things, in any scenario S, some team gets W star or more points. But it can't be I, because the very best thing that I can ever do is strictly less than W star. So in every possible scenario, of the outcomes of the remaining games, Team I is eliminated. It is not possible for Team I to be the winner. So Team I is eliminated. So that's one side of the proof of the theorem. Let's do the other side. Okay. So the other side is suppose Wi is greater than or equal to W star. Okay? So I want to exhibit a scenario in which Team I is in fact not eliminated. Team I has the most points, or is tied for the most points among all the teams. So we want a scenario where Team I gets the most points or is tied for the most. Okay? Well, let's start with S star. S star was a scenario. It was a scenario where WS star is equal to W star. So some team, in scenario S star, some team is actually winning, getting W star points. Okay? It might be I. If Team I gets W star points in scenario S star, then okay, then we're done. Because we've exhibited a scenario in which Team I has the most points of any team, although it might be tied with some other team. Okay? But if not, then, well, how could it possibly be in a particular scenario that Team I ends up with less than W star points? If Team I ends up with less than W star points, it must also have less than WI points, because WI is greater than or equal to W star. Then in S star, Team I gets less than WI points. Okay? So again, in S star, there's some history, some outcomes, which payoff pairs happened for which games, and when you look at what happens to I over all of those, I gets less than WI points. Okay? Because it's getting less than W star points, and WI is greater than or equal to W star points. But that means that we can go around to games, in each game where Team I does not get the maximum possible points. Remember, this is the scenario for the future games. So in each game where WI does not get the maximum possible points, we'll just change the outcome in that scenario to where Team I does get the maximum possible points. And what will we do for the other team is, in the change in the outcome to where Team I gets the maximum possible points, the points the other team gets will either stay the same or decrease. And how do we know that's possible? Because of monotonicity. The payoff pairs have the monotonicity property, so that when we improve Team I to the maximum possible, what we do for the other team is either leave it the same or decrease it, depending on what are the possibilities in that sport. Okay? So now, in each game Team I plays, change, and I'm talking about new games, because you can't do anything about the old games. Each new game team I plays, change the outcome, the payoff, to give team I the best possible, the best payoff. But don't improve or increase what the other team gets, in fact, what any other team gets. So when you do that, when you go around to each new game or remaining game that TI plays, and you change the payoff so team I gets the very best that's possible, but in doing so you don't increase what any other team gets, which according to monotonicity is always possible to do, then what happens is we have a new scenario. Okay. This gives scenario, call it S prime, where team I wins Wi greater than or equal to W star points. And no other team wins more than W star points. Because we started out with a scenario S star where the best team won W star points. And now we've changed some of the outcomes to where I wins more than or equal to W star, but because of monotonicity, no other team improves or increases, and so again, all the other teams at best are winning W star points. And so here is a scenario. So S prime is a scenario where I has the most points or ties for the most. Okay, so that's the proof of the theorem, that there is this magical threshold, W star, which if you could find it and compute it, you could then look at Wi for each team I and compare it to W star, and you would know under our present definition of elimination whether or not team I is eliminated. Is there a scenario where team I can win the most number of points or at least tie for the most number of points? And this ties all those questions together. Now, what I was mentioning earlier is that in a previous lecture we saw how under the baseball scheme, when 1-0 is on the sport of baseball, 1-0 is the only payoff, that we can in fact determine whether a team is eliminated or not by using network flow. And in fact, it's easy to see that a small adaptation of that approach computes W star in the case of baseball. So W star in the case of baseball, W star can be computed efficiently. It's also possible to argue that in the case of hockey, W star can be computed efficiently, and that might be left as a homework. In the case of European football, even though W star exists, this theorem tells you W star always exists. There is a number, a single number, which you can use to then determine which teams are eliminated and which are not. Computing that number is not easy. And although in this class we've not yet talked about NP completeness, it is in fact an NP or NP hardness. It is in fact an NP hard problem to compute W star in the case of European football. So in some schemes, in some sports, it's not so simple to find what W star is, but this theorem that we just proved says that as long as the payoffs are monotonic, this W star does always exist. Okay, so now I'm going to move into the second topic I told you about, which is we want to sharpen our notion of elimination. We want to know, can team I be the undisputed winner? Elimination previously said, can team I get the most number of points at the end of the season or tie for the most number of points? Now I want to know, can team I, is there some scenario in which team I gets the most number of points, strictly the most number, no ties, nobody else gets that number, okay? And what we had done previously in our proof of W star and in our network flow was all about determining whether team I could get the maximum number or tie, or be eliminated, meaning it couldn't possibly get the maximum number or tie. So now we're asking a sharper question. Can it get the maximum number? No ties possible. Well, if we look at the end of this, at least one piece of that question is easily answered. Let me erase the board here and put up one part that's easy to answer. So here's an observation. If Wi is strictly larger than W star, then team I can be the strict winner. That is, it wins, that means team I gets strictly more points than any other team. Any other team. And the proof of that is scenario S prime. Okay, so going back over to this board, yeah, thank you. Going back over to this board, we described a scenario, S prime, which was derived from S star, in which what happened was that team I wins Wi points, and no other team gets more than W star. So if it happens that Wi is strictly bigger than W star, if it happens that Wi here is strictly bigger than W star, then we have in our hands a scenario, S prime, where team I is the undisputed winner. Okay? So this proof, as a consequence, proves that if Wi is strictly bigger than W star, that in fact there is a scenario, S prime, where team I is the strict winner. Okay, so the question of whether team I can be the undisputed, which means strict, undisputed winner in some scenario is only unanswered if Wi equals W star. Because if Wi is strictly bigger than W star, then the answer was yes. If Wi is less than W star, the answer is no. It can't even tie to be the winner. It can't even tie for the most number of points. So the only possibility for Team I to be the undisputed winner the question is only of interest whether or not Team I can be the undisputed winner is whether or not Team is in the case when Wi is equal to W star. Then we don't know. Then it's still a question, and that's what I'm going to show you how to solve, again through network flow. But it's a more complicated issue than the previous one of whether Team I is just eliminated or not. And in fact, the first solution I'm going to give you won't involve network flow, and then, but it'll be clearly a polynomial time solution, and then I'll show how to convert that to a single network flow. All right, so let me get my notes. Now it's getting more complicated. I need to follow my notes. Okay, page 3. So, solution. Well, in this solution, we need some definitions. First of all, we're going to let S star be the scenario that we talked about before. Okay, so S star is the scenario where the best outcome, the team with the most number of points wins W star points. Let S star be the scenario as before, where the best outcome for any team, Ws star, is equal to W star. Okay? And of course, at least one team gets exactly W star points. That's what happens in the scenario S star. Okay. And we're going to let L star be the set of teams which each get W star points in that scenario. Okay, so in the scenario S star, at least one team gets W star. That all comes from definition. But it may be that there are additional teams that also get W star, and L star is going to be the set of all those teams that end up with W star points. Okay. Now we're going to need another definition. So this is given a scenario S. Let's just arbitrarily, so this is general. In a minute we're going to use the S star for this scenario, but first we're going to define this as a scenario S. Given a scenario S, we say team IR is reachable from some team I in S if there is a chain I to I1 to I2 to ... IR minus 1 to IR, where in at least one of the games, one of the remaining games, one of the new games in S, scenario S, I beats I1, and in at least one of the games in S, I1 beats I2, and in one of the games, I2 beats I3, and so on all the way down. So this chain where, okay, now I need to go over on this board to finish the where. There's a chain, I don't want to where, I want to such that. Such that in S, I beats I1 at least once, I1 beats I2 at least once, dot, dot, dot. So I R minus 1 beats I R at least once. And all of these are in the new games. In the new games in S. Because we're going to change the outcomes. We're going to go from S to some other scenarios. And we can't do that in the old games. The old games, the outcomes of the old games are fixed. But in the scenario S, we're going to say, well, if we look at that particular scenario, which is, after all, a description of, and we're talking about baseball here, so each game is either a winner or a loss. Here we're saying, in the win-loss record under scenario S, I beats I1 at least once, I1 beats I2 at least once, and so on. Okay, and that's what reachable means. Okay. So here's the algorithm. Remember, what are we trying to prove? We're in the case, look at the big picture again. We're in the case where we have teams Wi, which equal W star. So in particular, let's say Wi. Wi equals W star. And we don't know whether there's a scenario where team I is the undisputed winner. We know that team I, there's a scenario where team I is the undisputed winner or can tie. But we don't know if there's a scenario where team I is the undisputed winner. So what we want to do is try to, under the assumption we want to give an algorithm that can decide for us whether there is a scenario where team I is the undisputed winner. And so here's an algorithm which will create some new scenarios and some information about the teams, and will in the end tell us whether team I can be the undisputed winner. Okay, so here's the algorithm. We're first of all going to set scenario S to S star. So we start out with a scenario S star, which we defined, and L to L star. We also defined L star. L star is the set of teams that win W star points under scenario S star. Okay, and then while there is a pair of teams IR, no, actually, let me just call it IJ in my notes, IJ, such that I is in L and J is reachable from I in scenario S, and J gets less than W star minus 1 points in S. Okay, so this is baseball again. This is only in the case of baseball that we're solving this. So when I say points, you can also think of that as wins, how many wins they have. So here we are. We set S, the scenario S to S star and L to L star. But then, if we can find a pair of teams, I and J, such that I is already in set L, and J is reachable from I, according to this definition of reachability, but J gets less than W star minus 1, and this is strictly less than that many points in S, okay, under scenario S, then what we're going to do is we're going to start changing some of the win-loss. We're going to change the outcomes of games. Then reverse or change the outcome of each game on the path from I to J. Okay? And so with scenario S, we're going to find, we have this path that goes from I to J, and in that scenario, I beats the next element on that path under some game, and that one beats the next element on some game, all the way down to, in this case, J. But if we reverse, that means that I will now lose a game, lose to this next person, who will lose to this next team, who will lose to this next team, and so on. So the net result is that every team on this chain loses one game compared to what they had, except for the last one, which is J, which ends up winning one more game. Okay? So when you reverse all those games, L now equals L minus I. Okay? L started out by those are the teams that won W star games. And now we're making these changes where every team on that chain, except for the last one, loses a game compared to where they were. So since I had previously been in L, it meant that I had won, under the current scenario, W star games, but now it loses one, so it's not in L anymore. So L is equal to L minus I, and then S is the new scenario, or updated scenario. I would write updated if I had room here, but I'll just write new scenario. And hopefully that's readable when you see it on TV. Okay, so let me just give a cartoon of this, and this is the whole algorithm. Let me give a little cartoon of this. So we start out with the scenario S star. And in the scenario S star, there's a certain set of teams, L star, that get W star points. Okay? They have that many points. And then an I happens to be in there. But if we look at the games that were played, the new games that were played under S star, not the old ones that were already happened at the point when we're looking at the end of the season at this problem, there's a game, at least one game, where I loses to I1. I'm sorry, I wins the game from I1, and I1 beats I2, and I2 beats I3, and so on down to J. And of course, this whole business, it can do all kinds of things like that. And this is just I beats I1 in some game, I1 beats I2 in some game, and so on. So this is a whole And in fact, it doesn't have to be acyclic. I mean, it could happen, this team beats this team beats, and so on. Okay, but anyway, we have this graph here of beats, of the beating relation. And now we see a path from a team I to a team J, where J has strictly less than W star minus 1 points in S star. In that particular scenario, team J has less than W star minus 1 points. And now we're going to create a new scenario where this game, instead of I beating I1, I1 beats I. Okay? So I1 beats I2 beats I1, I3 beats I2, and so on, all the way to J. And so what happens is that this team I now, its overall record has fewer points. So now I has only W star minus 1 points, and J has at most W star minus 1 points. Okay, because by definition here, J had less than W star minus 1 points. So now we've taken 1 point away from I, we've given it to J, and, I'm sorry, I said everybody here loses. They lose and gain. So I, in the end, loses 1 point, J gains 1 point, and the ones in the middle, they first lose, but then they gain. Okay? So they stay the same. So what's the net effect? The net effect is that L gets smaller by 1 element. I gets taken out of it. And this new scenario is called S. And then we repeat. We look. So here's L, here's S. This is still the set that gets W star points, and we still look. I is no longer in there. We would look for another element where there's a chain to something where this element has fewer than W star minus 1 points in the scenario S. And then if we find it, then we'll do this reversal. And the consequence of that reversal is that this team will end up with 1 fewer points. This team will end up with 1 more point. But so this team goes out of L, and this team doesn't go into L because it doesn't have, it only wins 1 point. And it had W star minus 1, and so it doesn't, it had less than W star minus 1, so it doesn't get up to W star. Okay, is that clear what the algorithm is? We're starting with one scenario, and we're doing these transformations and getting other scenarios along the way. This process will terminate. The algorithm terminates because L is getting smaller by 1 element at each step. So L starts out at most having n elements, and is the total number of teams. And after each iteration of this algorithm, of the while loop in the algorithm, the set L gets smaller by at least by 1 element. So the algorithm terminates. Also, the algorithm is clearly polynomial. It's you're looking for these paths from an element in the set L to another element which has the property that has less than W star minus 1 points. And these paths are just based on the win-loss scenarios in the win-loss outcomes in scenario S. So we can certainly search for these paths and find them if they exist in polynomial time. So this is clearly a polynomial time algorithm. In the end, I'll show you how to do all of this, the entire algorithm, with a single network flow. So instead of being this iterations of this while loop, we'll just be able to do, we'll move from S star to the new scenario that we want in or the new end result that we want in one network flow. But right now we're describing it through this algorithm where we're doing transformations of scenarios. Okay, so knowing what the algorithm is, I want to prove a few things about the outcome. Definition, little l is the cardinality of L at the end of the algorithm. Okay, so ultimately, we were saying the set L is getting smaller and smaller at each iteration of the algorithm, and as long as we can keep finding these paths, we're going to reverse the games, the win-losses along there, and L is going to get smaller. So when the algorithm can no longer find one of those paths, then the algorithm terminates, and little l is the size of that set. Okay. Now, little l is greater than or equal to 1. Why is that? If little l, so there's at least one element when we end up. If not, then we have created a last scenario, the final scenario that the algorithm has, S, where every team wins, actually I'm going to put it that way, where no team wins W star games or more. No team has W star points or more. But that contradicts the definition of W star. W star was the minimum of the best outcome of each possible scenario. So there is no scenario where the best outcome, where everybody wins fewer than W star games. Okay. So L is greater than or equal to 1. So there's definitely somebody in that set there. Okay. Now we need one more definition before I can start proving things. All right, let me go over here. Okay. So here's another definition. At the termination of the algorithm, we're going to define T to be L union with the set R of all teams reachable from L. So again, L was at the end of the algorithm, L is the set which we know, as we just observed a minute ago, is not empty. It's the set of elements that have won W star games in the scenario S. And then we have these chains according to the definition of this team beats this team, and we could have chains from somewhere else, and so on. And everything that's reachable, this whole set here, would be R. We don't have the requirement that this team has one less than W star minus 1. That was part of the that was part of the condition for continuing the algorithm. If we were able to reach a team that had won strictly less than W star minus 1 points, then we would have taken this chain and reversed. Okay? So in fact, each one of these teams in R wins exactly, we know that they've won exactly W star minus 1 points, because if they had won less than that, the algorithm would have continued. If they had won W star points, they'd be an L. Okay? So, each team in R has won exactly W star minus 1 points, or games. I'm using points and games interchangeably. All right. Yeah. Okay, so this is just defining what we're looking at the point of termination. When the algorithm terminates, we have a set L and we have a set R. And we can have, of course, other teams that are not in either L or R. Now, the main lemma that's going to untie everything is the following thing. Lemma: in any scenario, where the winning team wins exactly W star points or games, at least L teams in T win W star points. So remember, we're looking at scenarios. We're asking about whether team I can be the undisputed winner if it wins W star points. And what this is saying, and where team I wins exactly W star points. And this is saying over all possible scenarios for the remaining games, if the winning team does in fact win exactly W star points, then at least L teams in T win W star points. Okay, if the team that has the most number of points has W star points, then at least L teams in T have W star points. So, as an immediate consequence, this is saying that unless L is equal to 1, no team can be the undisputed winner. Because in every possible scenario, you'll have at least 2 teams that have W star points. Well, no team can be the undisputed winner if it has W star points. We already handled at the very, very beginning of this the possibility of a team being the undisputed winner with more than W star points. But now we've been focusing on the question of can a team be the undisputed winner with exactly W star points? And this is saying only if it happens that L is equal to 1. We've got this algorithm which in the end computes a little l. And unless little l is equal to 1, there's no hope for a team being the undisputed winner by winning W star points. Okay, let's prove this. Okay. Let WT equal summation WI, little wi, for I contained in T. So this is the number of games that the teams in T have won before we're looking at the end of the season situation, before we're looking at the scenarios that finish the year. So this is the number of games that teams in T have won up to that point in time. And let G S of t be the number of games won by teams in T in scenario in some scenario, in scenario S, let's just say, where S is just some, okay. So in any scenario S that has this property, we're claiming, making this claim. And so now we're just going to look at how many games did teams in T win before we started this scenario, and how many games did they win in a scenario S. Okay? How many games did teams in T win in scenario S? Okay? All right. Got that. I need another board. Oh, no. This is the definition. This is the size of L. Okay, we can get rid of that. Little l is the size of capital L. Okay. Now let's look at, here is L, here's R. Okay, together these are T. And in scenario S, a team in T wins some games. Okay? In scenario S, a team in T wins a game. What game is it? Well, let's say it's a game like that. It's a game between somebody in T and somebody not in T. And this team wins. Okay? But R is the set of teams that are reachable from somebody in L. So this one would be reachable from somebody in L also. So this is saying, and of course, if we just went directly, like here, this would be reachable from somebody in L. So this means that every game, but T is maximal. We've reached, it's supposed to be all the nodes, all the teams that are reachable from L by some chain. Okay? So every game that a team in T wins, some team in T loses. Because again, if the game that they win is against a team that's outside of T, that contradicts the definition of T. So every time a team in T actually wins a game, it's winning from a team that's also in T. All right? Okay. Now there can be games like this where it's losing to somebody outside. That's certainly possible. Okay. So hence, in any scenario, the total number of games that teams in T win this is the total number of new games that teams in T win is at least GST. Because in a different scenario, what can you do? You can change the outcome of each of these games. But it's still one team in T wins and one team in T loses. You could change a game here, which means that a team in T wins now that had previously lost. So in any other scenario other than S, the total number of games is at least GST. Okay? Because that's what it was in S. All right? So So in any, I'm racing against the clock, I've got 9 minutes, I'm going to make it. In any scenario, the teams in T win at least, well, they win what they had won before the scenario begins, WT, plus GST. We were just arguing. And that's equal to T W star minus 1 plus L. Okay? Where does this come from? This is saying that every team in T wins at least W star minus 1 games. Well, we argued that that was true for the teams in R. They win a total of W star minus 1. And that's under scenario S. That's the scenario where the algorithm finishes. Each team in R wins W star minus 1 games. And how many games does each team in L win? They win exactly W star. And there are L of those teams in L. So this is the total number of games won by teams in T in scenario S, but we're arguing that in any scenario, the number of games that teams in T win is at least what it was in scenario S. That's what we argued a minute ago. So we've got that. So at least L teams in T must win W star games in any scenario. Well, this is just arithmetic. When I read this in preparing for the lecture, I went off to the side and did a little calculation. Suppose each team, suppose that there were L minus 1 teams that win W star and all the rest win W star minus 1. It doesn't add up to enough. Okay, I can let you do that by your own because we're running out of time. So instead of doing that, showing you that little calculation, I'll just tell you this is arithmetic which you can verify on your own, that in order to get up to this sum where we know that the maximum that any team wins is W star, that you have to have at least L teams that win W star games in order to get up to this total. And that's the proof of the theorem that we were saying, that in a scenario where the maximum number of points that any team wins is W star, at least L teams in T win W star games. And so we get several immediate corollaries which pretty much finish what I wanted to say, except for the network flow part. But here's a corollary. First of all, if L is greater than 1, then no team can be the undisputed winner with W star points. Okay? There could be some undisputed winners with more than W star points. We dealt with those at the very beginning of the lecture. But if L is, we have this algorithm which runs in polynomial time, and it computes a little l, capital L and little l. And if little l is bigger than 1, then there's no other team that can be the undisputed winner with W star points. Also, if L equals 1, so it's a necessary condition that L equal 1 for some other team, for some team to be the undisputed winner with W star points. If L equals 1, no team outside of T can be the undisputed winner. With W star points. Well, that's a triviality because L because what we proved earlier is that if there's some scenario where the maximum number of points that any team wins is W star, then at least L teams will have that property. So this is saying there will always be another team. If you're looking at a team that's outside of T, if it's going to be the undisputed winner with W star points, that's not possible because there's going to be some team in T that also has W star points. So we can avoid those ones. So what we're left with is the only possibility for a team to win, to be undisputed winner for W star points, is if L equals 1. Okay? So finally, we get another simple lemma. If L equals 1, then every team in T can be the undisputed winner. With W star points. And why is that? That's constructively from what the definitions are of T. Okay, so we'll just do a little picture here, which will basically show you what's going on in that proof. So we have L, which is just a single team now, and we have T. Okay, if it exists. We have R out here, which if it exists. Now, the single team that's in L, we found that finally under a scenario S, where it has W star points, and these guys have W star minus 1, or strictly less than, W star minus 1 points, and everybody else cannot possibly be well, anyway, I claim that under S, the final S, this is the undisputed winner. And because each one of these is reachable, you could then, from this team here, you can reverse all of these games, decreasing this by 1, increasing that by 1. These ones were W star minus 1, so when you decrease this one by 1, increase that by 1, this guy becomes the undisputed winner. And that's the proof of this last lemma. Okay, the end went very fast, but that's basically it, proving the theorem. The final theorem is that you can run this algorithm, which is polynomial time. If you get L equals 1, if you get L bigger than 1, then there's no hope for any team. If L equals 1, then precisely the teams that are in T, each one of those can be the undisputed winners with, under some scenario, a different scenario for each one, winning W star points. What I didn't show you is how to implement all this with network flow. And because this topic is under the heading of network flow, that's too bad. But it's also pretty easy to do it's pretty easy homework. So I'll leave that as a homework for you. And